We've all been there, in the middle of a job, everything going smoothly, until boom, you're missing a part. United Refrigeration is your one-stop shop for all your refrigeration needs. Use your computer or smartphone to go to www.uri.com at any time of day or night to check stock on your favorite brands, such as Copeland, Sporlan, Carlisle compressors, Danfoss, Emerson CPC boards and sensors, Carrel, Hussmann parts, and Co2. United Refrigeration Inc. is home to these brands and many more. Looking for information on refrigerant conversions or refrigerant banking? Quick access links on the homepage can get you to the information you need. All approved accounts are able to see live-to-the-minute inventory and pricing. Product not in stock at your local branch? No problem. Use the Nearby Stock feature to find a local branch that does have what you need. Are you looking for a branch address, phone number, or after-hours number? That's all available as well. Just click on the branch locator and search for your local branch. Have a model number and looking for a replacement part? www.uri.com/ARP has a vast list of quick pick replacement parts. Just search for the model number of the equipment you're working on and click the Replacement Parts tab. If you don't have an account, click the Register button and we'll have you online in no time. With more than 400 locations in North America, each United Refrigeration branch is fully stocked for immediate pickup. Our branch employees have in-depth technical knowledge, so we can help you get what you need when you need it. Visit your local store or www.uri.com/ARP today. United Refrigeration Inc. has all your solutions down cold.
John, how can you always have the right TV for the right application without carrying hundreds of valves on your truck?
You can carry the hundreds of valves on a trailer behind your truck.
That's too funny. That would work, but how are you going to do that? Maybe there's an easier way.
You can use Sporlan's interchangeable cartridge style Type Q and Type BQ TEVs. Type Q is a conventional design and Type BQ is a balanced port TEV.
Well, come on, I need easy. How easy is it?
Easy as 1, 2, 3.
And it serves thousands of unique applications. So what's the process? How do I put this together?
First, you select the thermostatic element assembly. Then you select the body that you need. Then you select the right size cartridge for the application to get the proper capacity TEV for your application. And then I guess it should also be said you want to actually assemble those into a single valve.
That'd probably be a good idea.
Indeed.
These easy to select and assemble valves mean you're always carrying the right valve for the right job then. If folks want to learn more, what do they do?
You can go to sporlan.com and find more information on the Type Q and BQ thermostatic expansion valves.
I guess that's Jim and John for Sporlan signing off.
When it gets bad, just remember the weekend's coming. Even if it's Monday. It keeps me going.
Be worse.
Good evening, everybody. Welcome to Advanced Refrigeration Podcast. You're here with your host, Brett Wetzel, Kevin Compass. What's going on this week, Kev?
Oh, kind of bouncing around and did some condenser change outs this morning. And I don't know, for the last 4 hours, I've been working on my personal vehicle, and I never want to be a mechanic. I hate dealerships. And yeah.
That sounds fun.
It's a bad time when my wife walks out in the garage and she sees a tap and die set and a welder sitting right next to the truck, and I'm just throwing things.
She's like, I'm stepping away.
She walked right back in the house.
See, I've heard, you know what, just recently I heard that you do get angry and you throw shit sometimes. You throw shit in the motor rooms.
Yeah, well, sometimes it happens.
You'll have that on those big jobs.
Don't act like you never threw anything.
I honest to God, I never have.
Like, dude, you just threw that filter across the room. Now it's disintegrated. Oh, man.
No, I've yelled and just as loud as I can. The one time I did, because I couldn't find this fucking short, and the store manager comes up. He's like, "Are you okay? We thought you got electrocuted or something. Something happened." I was like, "No, I'm just hating life right now. I've never thrown a tool or a refrigerant cylinder in anger." So
you should give it a try. It's a major stress reliever.
The whole holes in the back of my garage door from wrenches skipping across the garage.
Where'd that 10 millimeter go? It probably went 3/4 of the way through that 1/2 inch drywall. Well, tonight we got Joe Sigg from CoolSys Energy Design. He's going to be walking us through how to size different components on a CO2 rack, going from we'll do compressors and flash tank and lines and valves. Oh my, we'll do it all, right?
Yeah,
you good with that, Joe?
Yeah, absolutely.
So
yeah, hi, I'm Joe Sigg. I work for CoolSys Energy Design. We're part of the professional services branch of CoolSys, which is based out of Brea, California. They're a nationwide. Here's my plug. They're a nationwide contracting company. They perform refrigeration, HVAC, electrical, and plumbing services for a variety of different end users at this point, and they're always looking for more. Anyway, I'm the refrigeration department head over at CoolSys Energy Design. I'm directly involved with all the refrigeration work that comes in our door from an engineering, commissioning, construction administration standpoint. I deal with it all. So, I'm here today to talk about the mystery of CO2 systems and how they're put together from a sizing standpoint.
Go ahead, Joe.
Okay. Yeah, so when you're putting together a CO2 design for a client from an engineering standpoint, there really isn't a lot of difference from a DX system design standpoint to, when I'm talking DX, I'm talking synthetic refrigerants such as R4, R22, R404A, R448A, R449A, R47A, so on and so forth. Those types of systems designs are not that far off from CO2. There is certain things that you need to worry about or think about when you're doing the design for a CO2 system. And the one big thing that I'll just get into at a high level right now, when you're sizing a CO2 system, the first thing you need to do is you need to critically analyze where the location is that you want to put this system in. If you're talking south of the Mason-Dixon line, you really need to think about temperatures of climates and how hot it's going to be in the summer months of that area. CO2 has a critical point of about 86 degrees, and once you get over that critical point, the system will go into what's called transcritical mode, and the gas now becomes a multi-phase mixture basically. And it's not a liquid, it's not a solid, it's not a gas. You don't know what it is and what percentage of what constituent it is at that point. So what that does is when you're operating above 86 degrees head pressure, you actually start to cost a lot more money and energy spend from the system running, because the system has to work a lot harder to maintain that refrigeration effect in those connected fixtures, things of that nature. So when we size our systems, we'll use different technologies to overcome those hotter ambient conditions. For example, we just finished a refrigerated warehouse in Houston, Texas, which is the armpit of the nation. It's humid, it's hot, it's nasty. It's just a bad area for ASHRAE conditions.
Smells bad.
No, I'm not even getting into that because that doesn't affect refrigeration operation. But I mean, so what we did there was we opted to go for parallel compression, and we actually introduced ejector technology into that design, which we're working with an OEM partner, to put that into the system design for that location. And really, when it comes down to it, with CO2 systems, you need to worry a lot more about how much spare capacity you have on your compressors, your gas coolers. You need to look at your line sets critically, because when you go from DX to CO2, your line sets can get a lot smaller because CO2 has a lot more BTUs per pound than conventional DX refrigerants. You're going to get about a 3-to-1 ratio of BTUs per pound from CO2 to any DX refrigerant.
And you don't really get much subcooling in the flash tank, right? I mean, for the most part, it's usually maybe 1 to 2 degrees of subcooling. So wouldn't you run the risk of ending up getting flash gas easier in the liquid line because there's that little of subcooling? And that's one of the reasons, besides having a low saturated condensing temperature, but also insulating that line to prevent it from flashing because of that low subcooling, correct?
Well, so the reason that we insulate the liquid lines on a CO2 system is because the liquid coming off, due to the hot gas bypass valve that's coming off of the flash tank, that's set to maintain roughly whatever it's a preset temperature, but it'll maintain a certain temperature in that tank by relieving the gas off the top of the tank. typically what we size to is we size the 38-degree liquid, and we don't have to include a mechanical subcooler. And we just do that by utilizing the hot gas bypass valve and in conjunction with the head pressure valve.
You're referring to the bypass gas valve, the line that comes from the flash tank to the medium temp suction.
Correct. Exactly.
Okay. Just in case someone's like, well, what's a hot gas line? What's he talking about? I just want to make sure that we're on the same page.
Yeah. So that hot gas bypass valve, it is mounted. There's a port that comes off of the side of the flash tank, and it's mounted up pretty high so that it can catch the gas and not the liquid. And then that valve is a modulating valve that basically will modulate open and close to maintain a pressure inside that tank by bleeding off the gas to the medium temp compressors, the suction of the medium temp compressors. So again, when we insulate the low temp or the CO2 liquid lines, whether they're low or medium temp, we're insulating them all typically. And the reason for that is we're getting low temperature, or should I say, quote unquote, subcooled liquid temperatures going out to the fixtures.
Okay.
So that's another little intricacy of a CO2 system, is that you don't technically need mechanical subcooling if you program the system and set it up right from how you're running it. So, for example, the Hill Phoenix system, the Advancer system, automatically includes all those valves in its standard design. So as long as it's commissioned and set up properly, you don't need to worry about any kind of subcooling whatsoever, because you're going to get it off of the flash tank.
Gotcha.
Yep.
Yeah. Okay. And usually the reason why your load is so important is because not only do you have the load of the refrigeration for those medium temp compressors coming off of those cases, right? You also have the load from the actual low temp compressors discharging into there, right? You also have your potentially hot gas bypass for either load control or low superheat control, right? You potentially have liquid injection, and on top of all those things, your gas to liquid ratio versus when you're in transcritical versus subcritical. Like, so if you're running subcritical, from my understanding, it's usually about 50% liquid being created, and 70% liquid being created and 30% vapor. And then when you run that transcritical mode, it decreases because now your gas cooler is just that, it's just desuperheating. So now you have about a 50-50 mix versus liquid versus vapor creation. And you'll see more compressors run when you're in transcritical because of that, correct?
Correct, exactly.
Okay.
And what you'll see actually when you go into transcritical mode is you'll see that flash tank level drop because you're getting a mixed phase coming back rather than a full column of liquid. Your condenser, quote unquote, which is condensing the gas into a liquid at subcritical conditions, is now a gas cooler, which is only cooling the gas down as much as it can with the ambient conditions. Yep. So when we're sizing compressors for a CO2 system and gas coolers, we need to make sure we have enough spare capacity to overcome those transcritical conditions when the system is operating inefficiently, when the system is operating not at its peak. Typically on medium temp and low temp, doesn't matter which group, which type of load group you're talking about, we're looking at somewhere from in the neighborhood of 15 to 20% spare capacity on our compressors. That's what we're looking for.
Okay.
On standard DX systems, you're looking for anywhere from 10 to 12%. So we bump up that spare capacity because we know that when it gets to be 100 degrees outside, those compressors are going to have to work extra hard to make that system keep on operating the way it's supposed to.
So if you were to size it for the load of the cases, right?
Yep.
The medium temp compressors I'm talking about. If you would size it for the load of the cases, and then you would size it for the load of the compressors going into it, and then basically whatever that would end up being, you would add 20% for that transcritical operation. Is that correct?
Correct. Exactly.
That's a rough guesstimate, right?
You're in the neighborhood. Yeah.
Okay.
Yeah.
All right.
That's an educated guesstimate.
That's a what? Educated guesstimate? Yeah. Yeah.
Rough estimate when you're engineering things.
So I'll take an example of a project that I just designed. I had on my low temp group, on my medium temp group of the CO2 system, we were condensing at 87 degrees, which is actually in the transcritical range because you're above 86. We sized our compressors. We had a total load on that group of 616 and a half MBH. We ended up sizing the compressors for 789.5% or 0.5 MBH, and that gave us 28.05% spare capacity. And that helps when you're in the medium temp side of life. you need to consider that you need that medium temp in order to run the low temp. So if your medium temp fails, your low temp fails too. That's a critically important thing that everybody needs to consider when you're putting in a transcritical CO2 system. So let's see. So what I can do is I can kind of share. Let me share some stuff here.
Let's do it.
Share screen.
So while Joe's doing that, Kev, today I was making some training up, and someone told me they wanted a training for a certain customer, and they're like, yeah, it's liquid pump overfeed. And I basically got the liquid pump overfeed stuff doing, like I started making the program and stuff. And then I get an email with the program, and I'm reading through the program, like, wait a minute, this is like all the things that are usually in there, like the pump, all the pump stuff and the vessel, just everything. It was typically for a liquid overfeed system. And then all of a sudden I started seeing some like cascade stuff. Like it had a high pressure of like 480. And I'm like, what the hell's going on here? So I emailed them like, can you guys send me like some pictures? And here it's one of those systems that it's a liquid pump overfeed, but it's also a cascade all in one.
Yeah, we have a couple out here.
Yeah.
They suck to work on.
Well, I guess we'll find out.
You got all the problems of the liquid pumped overfeed, like the condensation issues, the insulation issues, the massive amount of CO2 it needs.
Yep.
Oh.
All right.
All right, so
Joe.
So this is a project that we just finished, and basically what I have open is I have my schedule open just to kind of show the loads that are connected to the system, the compressors that we chose, and just some salient features of the system. Showing at over on the other side here, we show the gas coolers that we selected, and we actually use de-superheaters on this project. A separate gas cooler that basically de-superheats the low temp gas prior to putting it into the medium temp group.
Get you.
That's such a tricky line to walk, especially like out by us.
Yep.
Like that could quickly turn into the compressor murderer 5000.
Yeah, what ends up happening, Joe, if the line gets too cold where it actually starts condensing in there, those heat exchangers do not like that at all.
Really?
Yeah, and then like if they get liquid that's created from the de-superheater, because we've had it just here in Texas.
Oh, Brett, these are like actual transcritical. What they're doing is they're running the low temp up through a loop of the gas cooler, and they use it to de-superheat, and then they dump it back in the medium temp, so that way it doesn't put as much load in hot gas into the medium temp.
Oh, but then if it does condense, that means those medium temp compressors are just going to get a slug of liquid.
Correct. We did a couple Costco's with that with zero. They had the valve set wrong the one time, and it was like 10 degrees outside. Was shaking as soon as the three-way valve opened up.
You start hearing the compressors going clunk, 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 clunk.
Yeah, they sounded like a 1986 Honda Accord
that hasn't been taken care of
with a belt wheel, just the squeal of death.
All right, so what are we looking at?
So what we're looking at here, this facility it's a large seafood freezer operation. Basically, they were what the scope of work was here is they have an existing facility, about 50,000 square feet. They're looking to put another 100,000 square feet beside it and expand the facility. So basically, what we were tasked with doing was, right now they have all rooftop condensing units, standard DX refrigerant serving evaporators in the space. They wanted to get rid of all that and go to a centralized CO2 system design. So we split the load up, the new loads and the existing loads. We did the whole thing. We put the loads on two separate systems. We have compressor rack A and compressor rack B here. And the reason we did that was just for redundancy. If one rack goes down or has to go down for service, they can keep half the facility up and running. We interlace the evaporators in the spaces so that they can keep temperature in the spaces while they're working on one of the systems. And that's one important thing to consider, because it's more important with a CO2 system than it is with a DX system when you're talking about redundancy and large walk-in spaces like this. Because, like I said, if you take down the medium temp, you're taking down the low temp as well.
So I have a question, because like everybody has a different flash tank pressure that they hold. Like I see yours saying 38 degrees, right?
Yep.
I'd have to get a PT chart out. I'm assuming it's going to be close to probably 520 or something like that. But
Aaron,
anyway,
I can bring that up right now. Just bear with me.
All right.
I'll tell you exactly what it is.
So my question is, why do some people do, that 38 degrees, and then you see some RS schedules that say 33 degrees? So what is the benefit, or why the difference in a flash tank pressure?
It doesn't, there is no rhyme or reason. There is no standard. Anywhere in the 30s is good. Some manufacturers prefer 33, some prefer 35. We've standardized on 38 because it gets you up near that nice 40-degree mark where you're not subcooling. You're not sending wild subcooled liquid out. It's just minorly subcooled, like a standard DX system. So
I would rather see it that high, because then you avoid the oil issues, you avoid flash off issues with the valve sizing, like running the higher, and it's more efficient.
True. Because your BGV is not opening up nearly as much. Yeah,
you flash gas load.
So as you guys can see here, I put in 38. Vapor pressure's 536. That's what you're looking at. Yep.
Okay.
So yeah, basically we went with Guntner because they're really good with industrial evaporators.
Yeah.
We like them a lot because they're single circuit. They're all stainless steel. They come factory installed with the Danfoss CCMT valve, which is really nice. Which is CCMT is the industrial brother of the AKV valve, the Danfoss AKV, which is the pulse EEV basically that's used in supermarkets.
So all the piping on this facility, is it regular standard copper? Is it HXP? Is it stainless?
We went with all stainless on this job.
Damn.
That's what the client wanted.
Do they orbital weld it, or do they do it by hand?
They're doing all welding, all welded copper. Yeah.
Hey guys, today's episode is sponsored by Westermeyer Industries serviceable oil floats. Many oil separators contain an oil float to effectively meter separated oil back to the compressors. Westermeyer Industries has taken this concept and perfected it with their new line of serviceable oil floats. These floats feature an improved design with fewer components, allowing for greater manufacturer consistency and up to 20% increased oil flow versus their legacy models. These floats also feature an integrated magnet to shield the oil path from debris and have been field proven in supermarket applications. Westermeyer Industries offer replacement oil floats not only for their own separators, but also cross-compatible models for our competitor oil separators as well. You can find out more about the Westermeyer Industries serviceable oil floats by visiting westermeyerind.com/floats. Once again, that's westermeyerind.com/float. Let's get on with the episode.
No, I mean, like, are they using the orbital welding machine, or are they actually TIG welding by hand?
Oh, no, they're doing it all by hand. Yeah.
Oh, wow.
Yeah, it's a long, arduous process, but that's what they wanted. So they wanted to make sure that they wanted them to do it by hand because they want to be able to monitor the process. The owner wanted to monitor the process and make sure that they're doing what they're supposed to do.
Damn.
Yeah. This owner is not a dummy. I mean, he knows what he's dealing with here.
Yeah, the from TIG welding, if they don't flow argon through there, like the amount of like soot and like they call it sugar dust.
Yep.
There is like 10 times worse than burning pipe copper without purging nitrogen.
Damn.
It's like this thick yellow soot.
It comes from the slag from the TIG, right?
Yeah, it's from that, and the air from the actual process of the argon when it's the TIG torch is using it, in the air on the inside, it like causes it to just condense and make that slag.
Oh wow, that's crazy. So what you can see here, I'm just going to show you guys my plans real quick. You can see we have these two large refrigeration enclosures. They're actually walk-in houses with the gas coolers and the superheaters mounted above there.
Are those abatic or are they dry cooler?
These are Guntner adiabatic condensers, adiabatic gas
Those
coolers.
are freaking huge. What's that? 2, 4, 6, 8, 10.
It's a 16 fan.
Damn.
Yeah, they make them that big. They do.
Well, that's huge.
You don't see, I mean, unless you work on industrial stuff all the time, you're not going to see equipment this big, right?
Yeah.
Like if you're working on supermarkets, you're only going to see a 2x3, 2x4, whatever.
It's been a minute.
Yeah.
Racks, or did you guys sub that out? to like one of the OEMs?
So we subbed it out to an OEM. We worked closely with them on the design side of things. We actually we picked an OEM. The owner agreed. We went with the OEM, and we made them comply with our design requirements. That's one thing that we do at CoolSys Energy Design that not a lot of other engineers I see do. A lot of times, you know, when you're working with an OEM, you get what you get because that's they strong arm you. You know what I mean? They say this is what we got and this is what you're getting. Well, no, I'm not willing to listen to that when it comes to me, because if I'm talking about a design, I'm already 3 weeks into it when I'm talking to you. Like. So basically what we did was we brought it, as you can see here, here's our pipe sizes kind of shown here. You know, we've got 4-inch horizontal suction, 3-inch liquid, 2-inch hot gas, supply and return.
Oh my God.
Yeah.
3-inch liquid. That's a lot of BTUs.
We got a lot of BTUs in this facility. I mean,
Shit.
This is just one side of it. Here's the other side. This is the new addition. Penthouse evaporators.
That's a lot of stainless steel. Oh, are those the out, like the one that has the owl on it? What the hell is that called? Wise. Are those Wise ones?
Wise? What do you mean?
No, the manufacturer, the Penthouse evaporators.
Oh, no. So the penthouses are getting stick built by the IMP lid, by the IMP manufacturer.
Okay. Oh, and they're just Guteners.
And they're just Gutener coils. There's no. It's just a bare coil basically.
Oh, okay. No, because like
with fan motors on the one side, and what we're doing is we're ducting it down and then shooting it out 45 degrees.
the reason why I was asking is because like when I did industrial, they had these Wise penthouse for like chocolate storage. You know what I mean, for shipping. And it's just literally a penthouse that just gets sat on there, and then just the ammonia piping just gets hooked up to the outside. Like we all came in like one big container. It wasn't stick built up.
So you picked it up and set it on the roof and then piped it up and you're done?
Yeah. It's insulated and shit, kind of like what this is looking like, but it just comes as one package, just sets right on the roof.
Wow, that's pretty cool. I mean, I'm getting ready to start up another project where we're going to be doing interstitial space penthouses above a new freezer. So we'll have to talk about that offline.
Yeah, for sure.
Yeah. So anyway, this is the new freezer expansion. 4 penthouses, 8 evaporators total, large industrial evaporators, centrally located throughout the space to even throw even airflow across the space.
Yeah.
We chose to go with keys for control with case controllers. We went with a Danfoss system because they're pretty much the leader when it comes to CO2 system control. I challenge someone to tell me differently.
The Canadians would disagree up north.
Oh, yeah, microtherma.
Oh, yeah.
Yeah, I know. As you can see here, we're showing all our sensors for defrost termination, the EV, return temperature, supply temperature, pressure, so on and so forth. All things you need: hot gas solenoid valve, liquid solenoid valve.
Who's the EMS guy? What manufacturer are you using?
Danfoss.
Oh, okay.
Yeah, here I'll show you our one line. So you can see it here. There you go, Danfoss AK SM880.
Well, that's what I was getting at. I was wondering what case controllers you were using to operate that. I didn't know if you went like I don't know if like Opto 22 has case controllers and shit. That's why I was asking. Yeah,
so we went with the CC550, which is the individual case controller. Only controls one valve to one coil. Danfoss had, keyword being had, the AKCC 750, but that's now getting phased out. They're no longer offering that. You have one right there? Yeah. Does up to 4 valves. Yeah. And they're now coming out with these new controllers. They now require 120 volt valves. And they're changing the whole game of how things are done from an EMS standpoint. So now going back to my legend. Wrong legend.
Was that a chicken?
Was that a chicken?
I don't know. Your background looked like a chicken or a rooster.
No, my background is my wife and I at our wedding.
Oh, that was really quick. I didn't see it that fast.
We got married in a brewery. So if you look closely, you'll see it's all the cans that are all lined up next to us and behind us.
See, I thought this was the red part and that was white. Never mind. I saw it really quick and I was trying to catch what it was. Sorry.
All good. So if we look here at how we size the system, this is the low temp side of rack A. You'll see that I only allowed for about 7.5% spare on the low temp. The reason for that is we're sharing some spare with the medium temp, believe it or not, because if the medium temp compressors are oversized, they're going to do a lot of the work that the low temp doesn't need to do. So you don't need to go as wild with the low temp as you do with the medium temp, which you see here. I got 28.5% on the medium temp, or 28.05% on the medium temp.
So you're doing conventional booster. You're not doing parallel compression, right?
Correct. We actually looked at parallel compression. This project is in New Jersey, so we didn't end up needing parallel compression because the ambient conditions didn't require it.
Okay.
Parallel compression is good for situations where you need to bypass gas around the medium temp compressors to keep the operation of the system up and running. Parallel compression is good for high ambient conditions. Situations where you're going to run transcritical most of the time. The parallel compression helps keep you down in the subcritical range.
So the ROI for a place like New Jersey wouldn't be beneficial, but you put a rack like that down in like Houston, Texas, you'd need that parallel compression to save the energy consumption versus what it would cost the equipment, the VFD, the compressor. You know what I mean, right?
And really, Brett, that's really what it all comes down to when you're designing a CO2 system. What you're trying to do, and what we've been trying to do over these last couple installations that we've designed, we're trying to prove to these end users that, yes, CO2 is the way to go as long as it's designed correctly. It'll be energy parity and possibly energy favorable to a DX system. Mm-hmm. And we have to design it accordingly so that they can see the proof in the pudding once it gets installed.
Gotcha.
Yeah. So that's where we stand right now. And then as far as the gas cooler is concerned, if we come over here, you can see that we still design it on a TD. We can see that this gas cooler has an operational capacity of 6,600 MBH.
And 10-degree TD, okay.
And a 10-degree design TD with an actual TD of 7.82. So we're right around, what a DX system would get you.
Do you get more total heat rejection? I guess you wouldn't. You wouldn't get any more total heat rejection out of a CO2 booster system as what you typically would, because basically you have less compression ratios, which means less discharge superheat, correct?
Correct, exactly.
Okay.
And you're circulating, you got to think about this, your mass flow is drastically lowered from a DX system. So you're not passing as much gas around the system as you would with a DX system.
What were you going to say, Kev?
No.
Oh, I thought you were... Sorry.
And the more gas that you have to handle in a refrigeration system, the more load it incurs on the system. Mm-hmm. When your refrigerant gets 3 times more BTUs per pound than a standard DX refrigerant, it's obviously going to be more efficient from every standpoint, basically.
Gotcha.
So, and then yeah, like we were talking about before with the desuperheaters, we specified a small 1x2, just standard air cooled gas cooler mm-hmm. for the desuperheater, just to temper the low temp gas coming off of those compressors.
That's a pretty big desuperheater for weighing 532 pounds.
Yeah, well, it's only 1x2, but it's got a pretty good amount of capacity because it's kind of tall.
Gotcha.
So yeah. Then if I go into let's go into I'm going to go to my calculations folder here. I'll open up some compressor calculations. So now, as you can see here, we have a couple iterations of our rack selections.
Gotcha.
One with parallel compression here. I'll open that first so you can kind of get a look at that. Now you see this is the Bitzer. This is right out of the Bitzer software. Mm-hmm. Here's the diagrammatic of the system.
Okay.
You have your low temp cases here, or low temp fixtures here. You got your low temp compressors over here. This is your desuperheater here. These are your medium temp fixtures here, and then these are your medium temp compressors here. This is your parallel compression right here.
Oh, so you ran it with that to see how much energy it would consume versus whatever in the high end or in the ambient that Jersey gets?
Yes, what I did was I looked at the COP of a system with parallel compression versus a system without, and it actually worked out in favor of not having parallel compression.
That's so cool.
Yeah.
I mean, I'm really lame, but that's so cool.
And then they guide you through the whole selection process. You can actually, the Bitzer software is really neat because you can select any combination of compressors. You just tell it how many compressors you want, and then you select how big you want them to be. In this specific situation, we didn't want 50 horse compressors across the board, So we went with more low temp compressors because they're easier to replace or easier to source and replace.
Oh, gotcha. Instead of having to get some big bastard.
Correct. Exactly.
Okay.
Now, there is a company that's coming in the door from Italy. Their name is Doran Compressors. They're coming in hot and heavy to the United States right now, and they have a wonderful offering for a compressor. They actually, yes. So actually, I'm not going to reveal any trade secrets, but the one big benefit I see is that they have a pocket inside of their compressor where all the discharge gas goes. It doesn't go into the main crankcase of the compressor. It's channeled into a separate cavity inside the compressor, and it keeps the compressor cool. It's very, very neat.
So that would be less total heat rejection then, right?
Less heat add into the system from the compressor itself. Like, you don't have to worry now about adding in the kW of the compressor into your heat load.
Oh shit, I didn't think about that.
Yep. Yeah, because we all know what the calculation for THR is, right?
See, I love talking to you because then it makes me realize how much I really don't know about anything.
The calculation for THR is quite simple if you know two things about your compressor. If you know the capacity of the compressor, and you know the kW consumption of the compressor, it's basically capacity plus 3.413 times the kW. That gives you your THR for the compressor.
Damn, I gotta write that down sometime. Okay.
And basically what you're doing is you're converting kW to MVH. That's it. And then added them two together.
Oh, that's all you're doing.
That's all you're doing. Yeah.
I just think Copeland will do it for me.
Hear that, Doreen? You need to get on it and get an app out so we have those calculations.
Actually, Doran does have an app, so I will.
Come on.
I'll send you guys a link when I'm all done with this.
God, I hate you. There's all this stuff you have and you don't share.
Yes, I do. I just don't share it until you ask for it.
Yeah, but I don't know I need it until you tell me it exists.
And that's why these conversations are good, right? So you'll see here one other thing that's different with the CO2 system that you're not going to see with the DX system. We like to size our compressors fairly evenly. We don't like uneven stepping, unlike supermarket designs where we like uneven stepping, because especially in this given instance, this is a large refrigerated warehouse. We're not going to have a lot of load variation, and we're not going to have a lot of steps in our capacity requirements. So we just size a bunch of compressors, all the same size, put a VFD on the lead, and off you go. Then you get 0 to 100% modulation because you have all your compressor size the same with one VFD. Ramp down, turn the compressor off, ramp back up, ramp down, turn blah blah blah, go on and go. Do it that way, basically.
Yeah, I got you.
Yeah. So and now you can see that I'm riding the line here I'm riding the line of the application window for the medium temp compressors. But this is one thing that they show you in the Pitzer software that's really neat. It shows you where your condition lies in the operating envelope of the compressor you're choosing.
You're living on the wild side for that first one, man.
Yeah, well, I believe that's the parallel compression. So,
okay.
So that's only needed in extreme situations, basically.
Gotcha.
And then they give you a little PT chart, kind of show you how the cycle works, basically. You know.
So let me ask you a question, because Jersey isn't not necessarily the most not humid place in the world. So sure. I mean, why a Baddock over dry?
So okay, so let me bring up my ASHRAE conditions for New Jersey.
I'm sorry, because I'm wondering, typically how much energy do you really get out of an Baddock? Is that maybe that's why you're only getting a 10-degree TD rather than a 5? It
really depends on your ambient conditions. And here's the kicker: when you're sizing gas coolers, the decision to go from dry to adiabatic really depends on the differential between your wet bulb and your dry bulb. If your wet bulb is 10 degrees or more lower than your dry bulb, go adiabatic every time.
One more time. If you said it again.
If your wet bulb, your ambient wet bulb on your ASHRAE printout is more than 10 degrees less than the dry bulb, you go adiabatic every single time because you're going to get the bang for your buck out of it.
Gotcha.
Right, because you're able to lower that head pretty far, right?
Now, I've always been kicking this around, like that you save a little bit of energy in the head.
Yep.
But your water costs are through the roof.
It depends on what type. Okay, So I'll address that elephant in the room. It really depends on what brand, what manufacturer of adiabatic gas cooler you use. If you use a Baltimore air coil unit, the Trillium, that recycles the water and only dumps once a day.
Correct.
Guntner and Evapco, they fill and drain continuously. So then your water usage goes through the roof.
So yeah, I mean, like in places like Chicago, like, I mean, we had a customer put a Guntner in, and it's using a massive amount of water. Well, they're getting a massive bill. So
well, that might have to do with the fact there's onboard controls in that gas cooler, right?
Yeah.
So it may be that piece of equipment never got commissioned properly, and it's just dumping. You know what I mean?
That's a high probability. Those things typically need to always be programmed. They send you that thing on the thumb drive and stuff.
They're programmed.
What's that?
They're programmed.
They are programmed. Okay. Yeah. Well, I personally, I prefer the BAC unit to any other manufacturer because they recycle their water. Yeah. They only dump once every 24 hours.
They are a nice unit.
Yeah, and they have the pads readily available for replacement if necessary. They have the EBM PAPS motors readily available if you need to replace them. They're not they're not a manufacturer that's not supporting their product. You know what I mean?
So check this out. When we were down in HR, we had a conversation. There was over in, I don't know if it was in Europe, but some places are actually starting to take their condensate water out of their cases because the solids are basically going to drop out. You know what I mean? So they have to briefly filter that water. Mm-hmm. They then use that water to refill the abatic.
That's a smart idea.
Right.
That's a really smart idea.
Think about it, because it's already going to be filtered. All the shit's going to fall out of it, and now you have nice cold water that you could basically just put in that abatic. So how much more extra capacity? If it's really hot out, we'll just let that water just pump up there.
Sure.
In like places like California where they're like dictators with the water, I mean that would be like perfect. That particular stuff was in South Africa. He was telling us that, Brett.
No, is that where it was? Okay, I could remember. He does stuff all over the place, so I can remember where the hell it was. We talked about so much shit.
Oh, let me close my door real quick.
That's the loudest door ever.
Not true. That door you have that you need to oil the hinges every time your kids open it. It sounds like a creaky old man.
Nice.
All right. So now we've gone through compressor sizing. We've kind of gone through the idea of adiabatic gas coolers versus dry. Mm-hmm. We haven't really gone through here. I want to take you through. Let me start up another session of my Microsoft Edge. I'll take you over to the Baltimore Air Coil site, and I'll kind of show you how they help us with gas cooler selections.
Oh, look, I know that site.
Yeah.